I don't know when do you want to.
Oh, so it's 4 o'clock, so you can start anytime.
Yeah, I think it's better if we connect on time, so we don't waste time, and it will be also better for people who are connecting in the broadcast, and maybe some people also on specialty and PhD will connect over there instead of using the Zoom platform. Okay, so basically, let's start. I take the initiative of introducing this webinar, which has been organized by Giuseppe and myself, and is a joint initiative between Karolinska and University of Padova, where basically Giuseppe and his staff will present their research on predictive modeling in the clinical area, and I will say in the oncological area more specifically. And so I will leave the word to Giuseppe to maybe introduce also his staff that will participate in this webinar. And so Giuseppe, please, and thanks for giving us your time today.
Yes, thank you very much. I hope that everybody can hear me. I will have my face for the moment, and then we go directly to the presentation. Together with me and during this seminar, there is Felipe Simao, that is from the GenVia Technologies. He's a bio statistical firms, and he will present himself when it's come his time. But I believe that at this seminar are also my collaborator, Lisa Villabona, and my other collaborators at the research level, Professor Rolf Levenson, I believe. Anyhow, if I may, I will start just for this seminar that is done in two parts. The presentation of by me, and that's mean that the most clinical part, and then a more statistical specific part by Felipe. I can present myself for those that doesn't know. I am a professor at the Karolinska Institute, but I am also a medical doctor, oncologist, since 40 years back, working in Sweden since 1977. And I was more or less involved in immunology, tumor immunology, since the university in Italy. And then when I came to Sweden, I could develop this part. This interest followed me all the way during all the years of what in oncology, and oncology had a lot of milestones. And one of these milestones actually was the discovering of the cytokines and the use of cytokines in human beings. But the most and unbelievable milestone is the one that brought to Nobel Prize, and it was about checkpoint inhibitors. This means that many things happen, in particularly for the melanoma. That was the first tumor that was used for this treatment. But you know, the treatment, all kind of treatments belongs to, they need to have some measurement, how you can see that the treatment is good or not good. And of course, since we are dependent on the farmers, we do a lot of studies, and these studies are preliminary studies and definitive studies divided in different phases that you go through, and at the end you decide that this drug is a good drug or not a good drug. I will make just a small let's say information that you can find papers what we have wrote about. There is a copyright for the name of the algorithm that we are talking about, and we have the papers that are supporting this. Anyhow, canonically, let's say, I would like to put it this way also. One is used to and has as a main question how a treatment is good for the patient, and usually we usually we are looking for an answer if the treatment is good or not, and if you have a comparison with other treatments, then you have an answer to this. This is the classical answer that we have to two products. They are this is melanoma patients, and treated with two kind of checkpoint inhibitors, and you see one is less efficient and the other is better efficient, but then if you use together, then you can better. So that's what you see. You are looking for overall survival or progression-free survival. This is the endpoint, the main interest that you can have. I want you notice that above of this curve that is empty, they are not giving you 100%, never. We never see this, but why? Because when you have a study, usually you put all the patients, you don't select more than it's necessary in inclusion and exclusion criteria, and you don't use particularly variables that can select the patients, because the interest is to give the drug to many people you can. You are not interested to see particularly groups. I, as clinician, and I am interested on this. So usually, what can I tell to the patients when they come to me and they say, I will give you nivolumab or ipilimumab, and they will ask me, is this effective? And I will say, yes, it is effective, but in 2 years, maybe you will have the possibility not to respond or so. I cannot give clear answer. I don't have good measurements at the moment that will tell me, yes, this treatment is good for you. This treatment is maybe, no, this treatment is not good for you. So in this curve, something is missing. We are not able to see the all through, and then we are not able to tell clear, to give clear answer to the patients. So all this presentation is based on the fact that 2018, we began a collaboration with our guest professor, Paola Scerto from the Istituto Nazionale dei Tumori in Fondazione Pascale in Naples. Why this? Because we are belonging to the same interest of immunotherapy for melanoma and so on. So at the end, after these two products of checkpoint inhibitors were used in humans, he had collected an amount of patients treated in any way, and we had a huge database, or almost not, but it was in the beginning of a database. And the main question at that time was, do we have the same results as it was given at the phase 3 information from the pharmas? Is it really like this? Because actually, I saw and he saw that it's not always so good as they promise. It's not 60% or it's not 70% as they promise. We have to see how is in real life, what we see in real life, and which are the method, not the methods, but the instrument that we could help us to go further and dig in the survival curve and to give much better information. And then we began to fill up a huge database of almost 600 patients of cutaneous melanoma. We had also other kind of melanoma, but we kept them outside. And at the end, when the database was done, we could see that this has been done retrospectively, that we could see that the patients could have a first challenge before being sent to the Pascale or from the Pascale itself. And we could group in at least five major groups, those that didn't have any treatment or they had before some treatment. And then they received either as first challenge or second challenge, one of these three checkpoint inhibitors. And then they have their stories, and you could have response outcome to this. Or if they didn't answer, they could have a third challenge. So this is it is rebuilt retrospectively, something that you could see in a possible clinical trials, prospective clinical trials. But you see that is quite complicated, and you should say, no, I would never do this kind of trials. It's impossible. It's too complicated. That's actually, it was complicated. Also, the analysis for me in the beginning, I did together with Gabriele Madonna, that is a collaborator of Paolo. And when I began to analyze just to see which kind of variables to use, I had big problems. So let's say I have something that always is here. Move this. Okay. Then I could see that if you see the old cohort, as you see like this, the ACE1 big cohort, all the patients with any treatment, not look at the treatment in the beginning, I end up with this kind of survival curve that is not so impressive. So let's say, okay, I want to see if the treatment, I could see if the treatment could make something. And of course, there is a difference if you see, and you see that you have the anti-CTLA-4 and the anti-PD-1 treatment. That's along with what you will expect it from the clinical trials. But the percentage and the results, maybe they are similar to what you see in the literature. But of course, I cannot expect myself something better in real life. Why? Because we don't select patients. We can have any kind of possibility. Also patients that shouldn't have treatment. But how can I see here in these curves, which are those that shouldn't have been treated? Let's go on. So what I had to do is to find out first if there were interesting variables, clinical variables. I didn't have omics. I had them later on. And of course, I find out all these were the possible registered in the clinical records variables that they put down. Some of these variables were known as predictive, some other completely new, some other from the literature. So it was easy for the known variables to have an idea if they were interesting or not for the outcome. So this is also what you have from usually from clinical trials, pharma clinical trials. They put this, they have a lot of variables. sometimes they correlate the variables with the outcome, but it will be a second or third endpoint for them and not so interesting. And usually they look at if they are interesting to, let's say, and forgive me, economical or distribution interest. If not, they will not care about that. So, and I understand this because it's a question of to sell it. But what I could realize is that one has to be very strict to define which kind of variables you have. So I taken from a paper I read before about something like this, I came to that you have to have the clinical variables. So there are many variables. They are subjective, objective, analytical, specific or not less specific, but they are bound to the human beings, that is the patient. Then you have variables that I call them intervention variables because they are coming to the patients and they change something in the patient's structure or in the patient's way of behave or come out. And this is the therapy usually. And all this for us is to see how they behave in time. So you have also the time-related variables, and you can have many that can measure what you have done on this with this variable. Usually, the knowledge of the subjective, objective, analytical, they are not so considered specifically. Instead, you look everything and you go directly to see how is the overall survival, as I told you before. So in front of this, what is the way of what's happened with this patient? So do I have a predictive instrument to see if what I did with this new, very revolutionary treatment can give to the Can I predict if I give ipilimumab, maybe I can have some patients that respond better or less better than other or so on. So let's see, I have the start of the analysis and look at this has been done retrospectively. So that's what I had in my hand. I have my start clinical variables, and then I have the intervention, and then I have the measurement, the time to relapse or time to relapse is related to a different time measurement is the time where you can measure a metastasis or the disease has come back. And it's different to time to disease-free survival because the time is the sensor as the overall survival. So there are two different ways to see the story. And then at the end, we have this prediction and prognostic related to the time variables, as I said. So we have the clinical variables, and there where I concentrate myself to find out if I could see something that could unify and give me an idea who is this patient started the treatment and what will happen. And then you see you have the clinical variables and the intervention variables here. Usually all the paper, so-called clinical paper related to survival or time to relapse, they look at for if this variable are important, and then they are analyzed by multivariate analysis with Cox, and then you can visualize them with a forest plot. And what can you say? You can say, yes, if you have a very high LDH, that's not so good. If you have a normal LDH, it's okay. LDH is lactic dehydrogenases enzyme in the liver, and usually is measure the amount of tumor you have also, and so on. If you have a CNS, okay, you have a very bad possibility to survive and so on. But all of these, also if they are hierarchically put together, they will give me a very, very narrow see of the story, they will not give me a complete story. That's what's happened, and that was my, let's say, light that came a very dark evening before Christmas 2019. Then I decided, say, why I have to find out the way out. And what I did is just I moved all these hierarchically way 180 degrees and just put them in this line. So all of them are similar to each other, but they have a different way to be. And what is this way to be? Is to give to them the possibility to express themselves. And yes, then I decide, okay, if I'm able to define what, for instance, this is the BRAF mutation versus the wild type, and see how they behave, looking for the time related variables, the survival. And then I see that the patients, they if they are mutated, they have a better overall survival than those that are not mutated. So I decide to give a weight. This one get a 2 and this one get a 1, based on the fact that they were significantly different using the log-rank Mantel-Cox test. Just to those that are interested, this is the idea of the Mantel-Cox. Actually is a chi-square analysis of those population that, of those cases that are alive against those that are not alive at the end of the measurement. And that's look like simply how it's put it in an Excel file, and then you have the cases, and then the put it the weights, so there will be 2 or 1s. But I have also found some variables that had 3 possibility, and then I used the 3 weight, the 3, the 2, and the 1. I never use 0, and then you will tell me why I wouldn't use 0. And then you see the log-rank Mantel-Cox is quite interesting and is significant. That's why I call it trichotomous variable, but that is the way for me to put them in an equal way. And this is another variable, if they received or not received target treatment and so on. And then you see if you have the variables here, and then you have the possibility for each variables here, and then you can have at the end a score. In this moment, this moment of the analysis, but together with Felipe, we find out other ways to go through this. I did not accept empty cells in the rows. That means all information should be there 100%. So I lost some of the cases from 578. I went down to 508, something like this, that they had 100% information on all the variables that I accepted. So that was how the algorithm was born, and I call it, at the end we found out this, there's several names before, but since it's an algorithm, by definition should have several steps. So these are 4 steps that form the algorithms. In the middle of this, you have the calculation of the score, and the calculation of the score is done by adding the weights and then divided by the number of the variables. Very naive, very simplistic, but I was surprised how was the results afterward. This is how it's looked like. If you take a patient, you have all this information that end up in a score, and then further on, and then there are all complete, that means 100%. if we analyze the results of this number of on these cases, yes, 503 instead of 578 that it was at the start. So I lost a lot. Surprisingly, I got only 1, 2, 3, 4, 5, 6, 7, 8 possibility numbers at the end, scores. And I expected much more, but maybe there is an explanation that I couldn't have more. And I expected very narrow, some narrow, let's say 1, 1, 2, or some. No, I just from the beginning, if everything is correct, it should be not more than this. Instead, if I had empty cells in the rows somewhere in the beginning, I did this test, yes, then I could have 20 kind of scores that it was almost impossible to group together. And then I could put together some of these scores and give a signature. At the end, I end up with 5 signatures that can distinguish themselves by their hazard also. Then I calculated 32 months that I thought it was the best. So that's it look like when you have the signature, very interesting. And what I could read out of this, yes, that if I look at by the hazard, the cumulative hazard, then I have that some of these signature belong to the unfavorable part, because especially these 2 signature, 1 and 2, that has very low score, that they have a possibility of get through very, very few. Instead, a group of signature that are very high, very good possibility of survival. And remember, these are second chances or first. They if you don't, as you've seen, only 40%, no, sorry, 20% at the end, they could survive. But I can see that if they had a good signature, I could really tell with a very high significance, that means very low possibility of error, to say that they should go through the whole treatment. What would I say to these patients? Maybe that we should see some of the treatment for some times and then see not go further and not to insist. And here you see 2 different treatments. And the interesting is that this fan, or let's say in Italian is ventaglio, or it's look like they are similar to each other in a way, similar behavior. And the end, the answer is that it doesn't matter which kind of treatment you're giving. And this is expressed here, you see, this is a interpose both treatment. Doesn't matter which kind of treatment you give if you don't have a good score, score, let's say, you belong a high signature, and only the high signatures can let you have a good response to any kind of treatment. So there were no difference. So you understand the impact in a way to talk to a patient, and you say, okay, if you have all these parameters and they have very good, it doesn't matter if I give you anti-CTLA-4 or anti-PD-1, because for sure you will answer. And here is also, if we look at the signature together with the outcome of the first challenge and together with the performance that you have. So high signature, high number of complete remission or partial remission. So conclusion, we could see that by retrospective analysis and using an algorithm, I could define signature in patients that otherwise would be treated without any discriminations from the this is what we are going also to validate now with the help of Felipe. Are you there, Felipe?
Yes, I need you to not share.
I will let you stop sharing and then you can share. You can go directly to the sharing.
Yep, 1 second. Okay, can you guys see it? So it's not able to see you.
Yeah. I silence myself now.
Okay, good. Okay, so once Professor Masucci was done with his idea of the clicker, he contacted us to further develop this idea beyond the initial scope, that the algorithm was based on this sum of the weighted scores, and there were some limitations of that, in that every variable or covariate is given the same weight. But in reality, some of these variables will have a higher impact on the outcome than others, like age, as you could see in the forest plot that Professor Masucci shared. So to further develop this, we decided to evaluate a few approaches, and we settled on a random forest approach, the SRF, the survival random forest. And so we started to develop this the clicker into the SRF clicker. So just go briefly over what is a random forest, just in case someone doesn't know. But a random forest is essentially an ensemble learning method that is based on decision trees. And you can think of decision trees as flow charts. So each node in a tree represents a point in the data, and each split is a split in the variables values, and this split tells us which downstream branch to choose as we traverse the tree. And following all these splits will leave us to the bottom or the leaf, which represent the predictions that we're making. And then we combine the random forest approach. It's called a forest because it combines multiple trees. And multiple trees become a random forest by a process called a bootstrap aggregation, or also known as bagging. So in this process, random forests generate new data sets by sampling uniformly from the original data set with replacements. So the algorithm trains each individual decision tree on perturbed samples, and using a random subset of features at each node that will determine which variable is used for a split. By using both of these subsampled data sets and subsampled features, the random forest can avoid overfitting by making the underlying decision trees less correlated, and then they allow the model to better generalize to new data and new situations. And once all these trees are trained in parallel, the random forest just averages out the results by a majority takes vote in the case of classification like we're making, and give us a final prediction. So in the end, the forest of trees will vote, and the decision that has the most votes will be what will be our classification. So a survival random forest is just an extension of the Leo Bryman's from the University of California random forest method that can be used to analyze right sensor time to event data. So like what we have here with overall survival of cancer patients. So survival trees and random forests are very popular for this, and they're non-parametric alternatives to other parametric models for time to event analysis. And some of the advantages of using random survival forests are that they're very flexible. They're fully non-parametric. They're able to handle high dimensional data. So like if we had a genotyping data or array data, this could also be used here. You don't have to use necessarily binarized clinical variables. They're able to automatically handle various intersections between covariates, so interactions between between each of them. And they're also suitable for when the Cox proportional hazards assumptions are violated in the samples. There are obviously some drawbacks. So main drawback is a bias towards including variables with many split points. But in the case of the SRF CLICO, since variables were already binarized by Professor Masucci, this main drawback is avoided. So a brief overview of how the SRF CLICO works is that the initial cohort is divided into two sets. Well, we select variables or covariates. So this was already done by Professor Masucci. We used the same variables that he's previously selected with his clinical knowledge. And then the cohort is split into two sets: the training set and the validation set. So the training set contains 80% of the patients, and the validation 20%. Then using the R package random forest SRC, we train random forests, and then using the validation set, we can compute statistics like the ROCs, and then we can predict survival. And based on the distribution of predicted survival probabilities for the patients, we can assign risk categories to each patient. So the random forest SRC is an implementation in R of the Bryman's random forest methods that can do a univariate, multivariate, unsupervised survival, competing risks, and many other analysis and regression types. And it also includes a suite of imputation methods. So what this imputation means here is that if we have patients for which data is missing, we can infer what the value of these variables will be for the patients using statistical models. We did attempt to use imputation for these patients that were missing data, so we could include more data for the model. And we also attempted just allowing the variables to be missing and not be used for these patients. In the end, the model without imputation worked, had an overall better performance, as imputing from this limited number of variables. So we have 9 total. There's not a lot of information to infer from. So this would be more suitable if we had a genotype style data like microarrays or whole genome sequencing, then that would be a bit more appropriate. So the starting point of the SRF CLICO is just a selection of variables. So Professor Masucci showed how this was selected using the Mantel-Cox analysis, and we replicated the results using the Cox proportional hazards analysis, and we have a very similar forest plot to what he showed in his slides. For training the SRF CLICO, as I mentioned before, we have the full data set, and we split it into 80% and 20%, 80% training set and a 20% validation set. Then models are trained using the random forest SRC. We tune the parameters. That means the number of trees, out of bag errors, and the number of tries for the trees, and the number of splits. And once we have this arrived at an optimized model, we compute statistics based on the validation set, predict survival times at 5-year time point for the validation set, and then use the distribution of predicted survival probabilities to assign the categories of risk. So if you have a quick look at how the ROC looks at the different validation validation sets, we have fairly good values at 0.07 for 12 years. 81 at 12 months, and overall the model performance only degrades at the 5-year time point, which is when most of these patients have already perished. To define the risk categories, we assigned, we used the models to predict the survival probability of each patient And this can also be seen as just a hazard ratio, so the inverse of the probability of survival. And using these distributions, we can see that for the melanoma cohort, there are two bimodal distributions and a tail. And using this, the boundaries, we assigned a high risk category, so patients with a low probability of surviving, a medium category that would be the intermediate, and then the long right tail of high likelihood of survival. We assign these patients to the low risk category. And then once these cutoffs are set, we use them for the new models for this cohort. Once we do this assignment of the risk categories for the patients, and we make a Kaplan-Meier survival curve, we can see that the behavior of these different risk groups is very different. With the high-risk patients, majority of them dying before 2-year time. The median risk category, there is a lot more patients survive than for the high risk, and then for the low risk category, there's a lot of the patients end up surviving by the 5-year time point, whereas for the high risk, everyone is dead by 5 years. So to validate these models, we used two approaches. One was the 10-fold cross-validation. So that is essentially splitting the data set into training and validation cohorts 10 times, each of them covered, so that each patient is used as the validation, at least once for the validation. It's a brief illustration there on the right, showing how a K-fold cross-validation works. You just split into validation and training sets iteratively in Windows until all the data set is covered has been used as validation. And then we also use for this cohort, it was possible to do this validation using an external data set. So Professor Masucci had a separate cohort of 170 patients, if I'm not mistaken, that could be used, that were from another study that had the same similar variables that we could use as an external validation data set, so data that was not included in the initial model at all. And we performed these two approaches and calculated, similar to what we did before. For the 10-fold cross-validation, we have a very similar ROC values for the average predictions over the 10 folds. And patients for this for the cross-validation cohort, the overall distribution on the Kaplan-Meier for the different groups is very similar, with the same pattern of high-risk patients dying before the 5-year time point, and the majority of low-risk patients still survive, with a median category that has a mortality, but a lot of patients still surviving. Similarly, for the 10-fold, for the external, for the validation with the external data set, we do see some drop off in the ROC values that we calculate. Those could be explained by the lower size of this cohort and the lower different distribution of overall survival across these patients. Though when we do look at the and Kaplan-Meier's of how these patients behave in the different risk categories, we do see that the three categories still split, in that high, medium, and low risk can be clearly seen, but there's the medium category in this in the external cohort is a bit closer to the high risk category, and a lot of the patients, there were very few patients in the low risk, which could explain why there was some degraded performance when we calculated the ROCs. In terms of what we expect for the future of this SRF FLICO method, is we would like to extend this approach to cover more cancer types and more data sets. So this could include using omics data. So far, we have already applied it to 2 other cohorts, colon cancer cohort and stereoscopic beam radiotherapy cohort. And for one of these analyses, we also did a model based on the time to relapse, not overall survival. And we did see a very good behavior of the model. So this seems to be a very easily generalizable approach that we can easily apply to different variables and different cancer types with patients that have missing data, either through imputation or not. And then the last point is to further develop this into a standalone application. Right now, all these analyses are done in R, so it's mostly a command line analysis. But we're now developing this a Shiny app, so that you can for the models that are already trained, you could easily just upload a spreadsheet or impute the values manually on a website, or a small application in a USB stick or something like that, and then easily run the predictions and assign the risk to patients in real time, and have them added to the Kaplan-Meier survival plots. And so this could be more easily usable by clinicians or anyone that is not familiar with command line interfaces. Well, I think if you guys have any questions, I would, both me and Professor Masucci, we would be happy to have a go at them.
You can leave maybe the sharing so we can see each other.
Thanks, Giuseppe, and thanks, Felipe. I think this is exactly hitting the mainstream of the research today: heterogeneity of an effect, personalized medicine, and so on. Well, I asked Danila Zolino, who is a friend and colleague from the University of Ferrara, to give a kick to this discussion. Hi, Danila.
Hi, nice to meet you. I am Danila. I have some comments and questions about your presentation. First one, we agree that the conventional method like Cox model or Kaplan-Meier representation may be not useful to evaluate the patient's predictive pathway, wherever there are many confounders that may impact on the patient's response to the therapy. I have a question and an idea to share with you. Do you think that in a well-controlled randomized clinical trial, is it possible to control all the possible confounders? Or maybe that there's a machine learning tool or instrument may be used also to enforce the possibility to improve the efficiency of clinical trial design. What do you think about this? And is there something implemented also in the melanoma cancer trial? And so I have also another question to pose to Felipe. What do you think about this?
This first question are to me, is it correct?
Yeah.
Okay. I'm very glad that you are from my old university where I did all my medical studies. You're from Ferrara, from the University of Ferrara. Yeah. Okay, thank you for the question. Actually, we have discussed, and Felipe just showed you one possibility to make clinical trial using an application, an app that using this knowledge, you can try. I have tested 10 patients together with my colleague and told her not give me the endpoint. So after 2 years of treatment, I had the variables in the beginning. I apply the algorithm and then look at where they would end up without knowing how it happened after that. And I tell you, it's almost 90 to 95% you get on the spot. And as Felipe said, we have tested this with the colon cancer, 600 cases, with a small study with radiotherapy, and another study that with the lung cancer, we tried this. So actually, there is a lot of material that we can study and develop. For sure, one important thing is where and how to use the simple algorithm, the clinical with SRF clinical, and why. I believe that they are complementary. In a way, for me, it's a selective way is to use the simple one. And then when you have an idea, maybe you can go through the validation, and then you should go through the validation. But we are talking now to do prospective studies. So the prospective study, think about it has to be very well programmed, where you have this algorithm prediction that is closed in a key for each patient, and then you go and look at what happened after 2 years. And then you open the key, they open and look at the key and what you predicted before. Okay. But there are other developments, actually, how to look at after the first treatment. If you look at again the same variables, how they would predict the next step, because now we have only at the start. And this is very important because suddenly you have this ventaglio of possibility that make you thinking if it is possible to use it in clinic and not in clinic. When we decide the therapy, we say that, okay, the patient has very high LDH, maybe we should not give the treatment, we should try something else, we give target instead. So, but it's not very well proved. I mean, it's just going by guts and how you're feeling. What we are looking for is to have instrument that can make it the life easy for the doctor, but also give to the patients more certainty. Now, what I tell you, oh yes, I have very nice treatment, but I put this but. What would happen? I cannot promise 100% success. That's the point. Instead, okay, with this, if this is applicable and then everybody can try, then we can say, okay, before you talk with the patient, you have the idea how it's look like with all the variables that you can have, omics, whatever. And then prepare your talk with the patient, say, okay, maybe you shouldn't go through this treatment. We can maybe follow you for 2-3 months, but I'm for sure if it's not working, we have to change. And maybe you follow the patients that has a very low signature to very much more often than usually you do. That's the point. We have not put side effects information that could more increase the possibility. This is variables that we have not considered. Maybe you have the question for Felipe, isn't it?
Okay, thank you, Professor. I have a question about the missing data imputation methods. How do you input your data? Do you think that your data are missing at random, or maybe that some patient characteristics may impact on the missing mechanism, and the missing imputation method may impact on the results of your random forest estimates? Is it true? It is an hypothesis. What do you think about?
So for the imputation, there are two ways that the package we use, the random forest SRC, can do it. It can do a very simple imputation based on just the frequency of each variable for its own variable. But it's also possible to calculate it based on the correlation of the other variables in the set. And we attempted using both of these for this cohort, and we evaluated the performance in the same way of the variable importance plots and as well as the ROCs. Mm-hmm. And what we found out was that imputing the variables was yielding worse predictions than just allowing them to be missing. The thing is that you have to remember is that a lot of variables, while we have 9 variables, the top 3 variables contain a lot more information than the bottom 3. So it really depends on what variable is missing rather than that there is a missing variable. And while for this analysis in particular, imputation wasn't very valuable. For other analysis, like if you do a GWAS, then you have many more data points to infer from. So this ends up being more valuable and actually adding positive information to the analysis. So it's hard to know in advance whether it will be valuable or not. It's good to try both, not imputing and imputing, and then deciding afterwards.
Do you have many missing data in your?
No, there is not a lot of missing data. From the
okay.
570 patients, there's about 70 that have missing data, so 500 are fully complete. And for patients that have missing data, at most 3 variables are missing.
May I say, you know, it is a question how the data has been collected in the clinical records, and for sure some medical doctor forgot to put down or to check for something and it's not there. So that's why it's very difficult to work with a few patients when you do a retrospective analysis. We are lucky because we are more than 500, so this 70 is 10-12% of the story. So, but for sure, they have an impact, but not relevant impact on the results. But we have to work with a lot of patients to say this, especially if we look at different new diagnoses that we don't know anything about. We have to have a substance and have a full cells database as much as possible.
Okay, if it's possible, I have another comments. But do you, if I understand, you perform the variable selection by considering a box, a backward elimination or something similar. Why do you perform this strategy instead of another strategy based on machine learning technique? Also, random forest is able to evaluate the variable importance measure or minimal depth or similar. Is there a clinical judgment behind this choice?
So for the case of the SRF was well, we were working with already selected variables, but since the variables we're using were already selected by Professor Masucci as being clinically important in the previous analysis. So that was the main reason. We did use the variable importance method, so that's calculated by the random forest as well. And so this was not shown on the slides, but the only variable that had not a lot of impact, let's say 0.02, was age, which was minimally important.
Okay,
so
thank you.
No variable with a negative importance there.
Yeah, that's
and this is for one of the other studies we did from Professor Masucci, the one that had last patients for time to relapse in the stereoscopic beam radiotherapy. For that one, we did see a few variables that had high negative values, and these were then not included in the final study.
Okay, thank you. Only another comments. I think that melanoma disease, it's not it's unfortunately a common disease among population. But when you perform your analysis in your data, do you have to deal with some problem of class imbalance or similar that you have to deal with? It's a problem that, is it a problem that you have to deal with, or in this case it's not an issue that you have to control?
Is it to me?
To Felipe.
You mean socioeconomic class?
The imbalance, the possible imbalance between the classes. Do you face this issue when you perform this analysis?
There is no information in the variables.
Yeah.
No, the class imbalance when that or characteristics is poorly represented in your data. So there are some issues in calculating and estimating your model performances. Do you have this problem, or is it all okay when you estimate your random forest?
So we didn't see any main problems in the melanoma cohort with the class imbalance. So for at least this model, this was not a particular problem, though it's something that we do have to keep an eye out for when creating models for other data.
Okay, thank you.
Thanks, Felipe and Giuseppe. I have seen that Corrado raised his hand. So, Corrado, maybe you have some questions or comments?
Yes. So, thank you for the presentation from my side too. It was very interesting. And I have a question to both of you. So, a similar question from the clinical and technical point of view. Regarding the selection of the variables. So at the start, you perform a quite focused distinction on the type of variables in clinical, interventional, and timing. And so I asked to myself if if selecting the variable for the model is a technical needs or a clinical needs, and given that once the model is created, clearly it can work only on the selected variable. So is that also from the clinical point of view a suggestion on which patient characteristics or study characteristics have to be collected because they are important for the model, or on the other side, if the unselected variable can be considered not relevant information to be collected. And for the other side of the technical part, once you decide to select the variable, how there was a clinical or computational threshold to decide I retain these variables or up to this level, or
Okay, maybe I answer you for the first part, but it's very relevant question because we discussed a lot together with Felipe so one of the main, if I am summarized, is how critical is the selection of the variables in all the system, okay? At the beginning, I didn't know anything, which one are the variables that are important. Actually, if you read a paper, a classical canonical paper of a clinical trial, they mix clinical variables with impact variables to look at the survival. So in the beginning, when I behave myself as a canonical way to look at this, but I didn't get the answer. I got a lot of answer, but not a comprehensive answer. So just keeping separated what you are doing in the process and make an order that you have the individuals, and then you do something with the individuals, and then you look at what's happening in the time. So that is the clear idea I have. You can mix and you can measure the intervention with the variables afterward when you have a clear cut what the variable has for significance at the end point. Because then you have the answer if the intervention is useful or not for the patients. That is my. Then, if I left out variables, for sure, those variables that didn't have enough information were not included. And what's happened with the variable that has no impact? That's what Felipe can answer you. With this system, both the clinical and SRF clinical, in the way, any information you have from any variables can be important to have a final score and could have more or less impact, but at the end give the chance to each individuals to have a position given by relevant or irrelevant variables. So it's not like the multivariate variables that you kick off those that are not significant and you keep only those that are significant. So I believe that in one of the analyses, there are variables, a couple of variables, yes, in the melanoma, also in the colon cancer, where we keep those that are not relevant. You can answer, Felipe.
Yeah, so the way we select these at the end, I mean, we could just plainly use the ones that were clinically curated already by Professor Masucci, but we can also evaluate this by the variable importance measure from the random forest. And this type of unsupervised selection of the variables is feasible. It's more, well, let's say it's what you should be applying once you have a lot of variables. Like if you have hundreds, you won't be able to curate them as based on expert knowledge, like what was initially done in this project. But variables that end up with high negative importance, once you do the VM calculation, these shouldn't be included in the model at the end, as they will actually degrade model performance. So with regards of how important it is to select the variables, well, it's very important. It will what you feed in the model is will impact what you're getting at the end. So, well, Professor Masucci said, we do include variables that were deemed not significant by the Cox-Bento analysis. But once you look at the variable importance, they are still positive values there. So they still contain some information, even if the age is not doesn't have a very high impact in the prediction. It still has a positive impact in what the model is predicting.
Thank you.
Thanks, Felipe and Giuseppe. And I don't see anyone else who is willing
We lost you.
to make questions or raise comments. Confirmed, I think we can end up this first part. And I just remember to those of you who got a link and an invitation for the subsequent meeting to quit out of this meeting and go into the other Zoom link. And if there is any problem, just drop an email to, I would say, Corrado to fix any issue. So thanks again. I think this was very helpful, and hope this will be one of the first initiatives that we will develop jointly between our universities. So thanks again, and see you next time.
So to the next videos. And okay.
See you.